And our next speaker is Melissa Hobson, who will be speaking about planets at the stellar rotation period from Espresso and TESS.
Hello, can you hear me? Great. So yeah, as Marlene said, I'm Melissa Hobson. I'm a postdoc at the Geneva Observatory with Francois Boucher and Christophe Lovis. And I'll be telling you about some fun I've been having with some Espresso follow-up of the TESS transiting planets. So, right. To give you a quick outline, first I'll do less an introduction, more a reminder about some characteristics of TESS and Espresso I'd like you to keep in mind. The meat of the talk focuses on, there's the pointer, the TOI 2322 system, its stellar characterization, and fitting it with both the Juliet and Pianetti codes, and some conclusions of future work. So let's get started. TESS, as I hope you all know, is the Transiting Exoplanet Survey satellite. It's been active since 2018 and observes one hemisphere of the sky over a full year in, sorry, I keep pressing the wrong thing for the pointer. In 27-day sectors, covers most of the sky in sequence. It has done 3 missions so far. And one thing I want to highlight here is that targets that are close to the ecliptic poles, so the targets at the top and bottom of these plots of the 3 mission coverages, will have practically a year's continuous coverage in each mission, allowing us to identify longer period planets. The other thing I'd like you to keep in mind is that TESS has 2 cadence modes, the full frame image, which stacks every 30 minutes, and for some selected targets, primarily bright stars, 2-minute postage stamps, from which we get both simple aperture photometry, which is what it says on the tin, just photometry, no detrending, and the PDC-SAT photometry, which has been detrended from long-term effects. Now, the other half of this talk is Espresso. So Espresso is the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, an acronym. It's on the Very Large Telescope in Chile, where it can take light from any of the 4 UT telescopes, or all 4 combined, but this data is all from single UT mode. It achieves, ultra-stable, very high signal-to-noise observations for extremely precise RVs, and we also extract many activity indicators. The work I'm presenting here is in the context of the Espresso Guaranteed Time observations, which were carried out by the Espresso Consortium, primarily between 2018 and 2023. The GTO observations are divided into several working groups. This is specifically in the context of Working Group 3, which is the Transiting Candidates follow-up, which over the years the GTO was active, gathered around 2,700 spectra, has already published 42 planets with focus primarily on the super-Earths and mini-Neptunes, the small planets where we really need Espresso's exquisite RV precision. There are also around 10 single system papers in prep, one of which is the focus of this talk. On the TOI 2322 system. So TOI 2322 is a star with a V magnitude of 11.9. From the Espresso spectra, we derived atmospheric parameters. We have an effective temperature of around 4,600, so a K4 star, nearly solar metallicity. And using these atmospheric parameters, plus the broadband photometry and the parsec isochrons, I also derived a 0.7 solar masses mass and a 0.6 solar radius. This star, this is why I was reminding you about the areas of full coverage in TESS. In the prime mission was observed in 12 out of 13 southern sectors. However, it was only observed in the full frame images, so 30-minute cadence. For the extended missions, however, it was upgraded to postage stamp, so we get a much better sampling with the 2-minute cadence in 12 sectors in extended mission 1 and 8 in extended mission 2. From this vast wealth of photometry, the TESS Quick Look Pipeline team identified 2 candidates. First, one at 20.2 days with a radius of nearly 2 Earth radii, and later a smaller inner candidate, TOI 2322.2, at 11.3 days with a radius of about 1 Earth radius. This numbering rapidly gets very confusing, so I will just refer to them as the inner and outer planet. We followed this up with espresso spectroscopy. We got 33 observations between November 2022 and March 2023, so just one season of observations, really. We reached a signal to noise of 48, which corresponds to a typical RV uncertainty of 1.2 meters per second. And here I'm showing you just the RV time series. The green and purple lines on this periodogram correspond to the inner and outer planet, respectively. That's a lovely peek at the period of the outer planet, isn't it? Now, if that were everything, I wouldn't be showing you this target at this particular conference. Let's take a look at the activity indicators. There's the CCF contrast, H alpha, S Mount Wilson, the full width, the bisector, sodium, log R prime HK, all of them with very, very prominent signals at almost the period of the outer transiting planet, and some of them even with signals at very close to the 10-day period of the inner transiting planet. Delightful. Now, if we'd seen this in a pure RV survey, I would have said, okay, it's a false positive, it's stellar activity, get rid of it. But we've got the transits. We have 20 sectors of test photometry saying there are planets there. So let's take a deeper look. Well, first thing, I wanted to see if I could also see evidence of stellar activity in the test photometry. So these are the PDC sample light curves, which are the ones I generally work with just because they're detrended from a lot of the instrumental effects. It does look like there's some variability there. Let's take a look at the undetrended light curves. Massive, very clear sinusoidal variability in all the SAP test sectors. Here I'm just showing the extended mission, so the 2-second cadence data, because there's so much of it, I don't need the 30-minute cadence. So let's try and measure the rotation period of this star from the photometry from the activity indicators. The espresso full width data, as I showed you before, peaks at about 21.3 days. The test SAP data peaks a little shorter at 20.8, but we do have the sector gaps, the changes in CCD, the instrumental effects. So I also want to look for ground-based photometry, specifically at the Assassin survey, which has observed this star for about 4 years, I think. And if we make a periodogram of their photometry, we get a very, very strong peak at 21.28 days. So I conclude that my rotation period is that 21.3 days. Let's now try and fit this data. My first attempts were some fits with the Juliet code, which was developed by Nestor Espinosa. And yeah, Juliet allows for joint fit of RVs, transits, and Gaussian processes. Now, I want to use the Gaussian processes precisely to detrend from activity. I have a lot of test photometry, like I said, 20 sectors. I would like my computer to not catch fire while I'm running these models. So what I do is pre-detrend sector by sector with the out-of-transit data, and then take only these points in red around the transits, applying the detrending that I fitted on the out-of-transit data, which reduces it to a manageable data volume. For the RV GPs, I do fit that simultaneously with the planets. I'm using the quasi-periodic kernel. The rotation period prior obviously constrained by my rotation period. To constrain the rest of the parameters, I first fit a GP model to the full width at half maximum and use the posteriors of that as priors to my RV GP. Tested several models, having only the inner planet, only the outer, both planets forced to be circular, both planets with free eccentricity. The favored model, which is the one I'm showing in these figures, is the 2-planet circular model. I'd like you to focus here on the semi-amplitudes. So we don't get even a 3 sigma measurement. We can't really confirm these planets' claim masses. So this detrending is not sufficient. So I decided to use instead a slightly more complex but better approach. Using the Pianetic code developed by Oscar Barragan, here I'm jointly modeling the test photometry, the RVs, but I'm now adding simultaneously into the model the full width and the bisector, using multivariate GPs in the framework of Rajpal et al., where I describe my RV, my full width, and my bisector as a linear combination of the same GP and its derivative. Again, using the quasi-periodic kernel. Here you can see in the top panel, the fit to the RVs, in the middle panel, the fit to the full widths, and in the bottom panel, the fit to the bisector. And once again, the rotation period of my posterior on the rotation period is of 21.4 days, very close to what I would expect from the photometry. And here we have the face-folded photometry and radial velocities, where we get values for the fit that are very compatible with the Juliet results. They're in agreement within the error bars, but they're much more precise. In particular, I have 4 to 5 sigma measurement on the semi-amplitude, so I can really get masses, not just mass upper limits for these planets. So to wrap this up and tell you about some future work, so yeah, the 1GP model is clearly not sufficient to model these very large stellar activity signal very close to the planetary period. But using the multivariate GPs, these are a powerful framework for modeling stellar activity, even in this kind of worst-case scenarios. The other thing which I forgot to write on my slide is it's incredibly important to have the transit photometry, because this is what's anchoring our period super precisely and letting us separate it from the very close but not quite the same active rotation period. I like to apply this analysis to similar targets. We have a couple more in the Espresso GTO dataset. Not quite as strong as this one, so this was why this was our test case. I'd also like to monitor these targets over longer timescales, so we only had 1 season of observations for this target. I'd like to see how the activity evolves over time. Also potentially use near-infrared spectroscopy, like with NERPS, which Alejandro very kindly presented for me, because we expect the activity to look different across different wavelength ranges. A couple of open questions as well. First, why are these planets so close to the rotation period and its harmonic? This could just be pure coincidence, but maybe there is something more there. And finally, how many planets like this are we missing in RV-only data, where we look at these very close signals and go, it's all activity, let's toss it out. And with that, thank you, and I'll take any questions.
Questions from the audience? I see one here.
Hi, thanks, Melissa. Could you go back to where you were showing the parameters of the planet?
Sorry, which one?
Where the parameters, mass, period, radius?
So, yes,
yeah.
there, that one.
So for the top part, well, and even the bottom, you're getting a 5.5 Earth mass for a 1 Earth radius. That makes it denser than pure iron.
Yeah, this is preliminary. Like, I'm still
figuring
out what's going on with that one.
So we were wondering, because your GP period is so close to the period of your planet, are you, rather than the GP absorbing the planet, is the other way around actually happening? Because
I suspect this is possible. Like, yeah, this is still a preliminary fit. I was working on it up until I sent the slides and then decided not to touch it anymore until I get back. But yeah, I am still confused by that one. I do think, like, so that's the inner planet where the signal is a lot less robust. I think the outer planet is a lot more of a robust detection. The RV signal is also much clearer. But yeah.
One more quick question, if there is one. Okay.
Great talk, Melissa, thanks. So my question is the same question you put up at the end of your conclusion slide. For those of us working in the RV field, are there any lessons to be learned about how to maybe know if we're incorrectly chalking something up as a false positive?
So, I mean, I can give you a slightly tangential answer. I did try running a fit on the system without including the information from the transit, so with a broader prior on the period and the epoch, and yeah, I do not retrieve the same system. I don't retrieve it with the same accuracy. I don't know how trivial it would be to debias this without having the transit information. Yeah, generally in RV-only surveys, something like this we do discard.
All right, let's thank Melissa one last time.